So then I will try to give you a number of applications. I've actually went around quite a number of PhD students and see what they have done, etc. And yeah, so there will be a number of different small pieces. But they have, some of them are around planning and energy reduction. Others are more related to this autonomous driving. And also I will end up with some more medical applications and health aspects. So I mentioned before about these robot applications where we have tried to minimize the energy. Another area which is quite interesting is AGVs, these automatic guided vehicles. And you see a couple of them here. It's from it's a local company here in Gothenburg, but they are owned by Toyota, and they are delivering AGVs for, in this case, for Volvo cars. And for the robots, it's critical with the accelerations and high velocity and so on. That is not the problem for AGVs because they are generally going very slowly. So it's more to find the optimal path that can and distance, optimal distance, which is the more critical thing there. So then the optimal routing is more focused on. But my former student, who is now working in this company, Sarma Driazzi, who also worked actually on the robot energy consumption. He argued here that it's possible to save energy up to 20 to 40%. So here it's just another picture showing these AGVs, and here you see what they transport there. Then related to this AGV, my colleague Martin Fabian, together with Sarmad and some master students, they also looked at how to use these supervisors to avoid deadlocks in AGV systems. Because deadlocks in AGV system is a very typical situations, and they have a number of rules trying to avoid deadlocks, but there is no systematic procedure to avoid deadlocks. So in worst case, they have to return to some places, and because they can go in backward direction and so on. But without giving the details around this, I just tell you that, well, this is an application where you have a storage area with a lot of transportations around. And then there are actually driving patterns for these AGVs when they go to these docking stations. And then if there are more than one AGV in the same area, there is a risk that they are staying and just waiting for each other. So here it's illustrated that in some specific scenario here, a deadlock could occur. And this type of rules that are coming up based on these scenarios, which are described here, they are giving the deadlock avoidance policies for these AGVs at the moment. But we suggest then something more sufficient or efficient, and that is to use our tool Supremica, which is nowadays especially developed by Martin. I mentioned about Martin and Knut, and Knut has moved more to the optimization area, but actually Knut was the first to start this project to generate this tool Supremica, and then Martin has taken over. And here you see actually the interface for Supremica. And you see these green, yellow, red light dots above here. And it's a symbol for that Supremica is a supervisor function which can show red or green. The yellow, I think, is more from aesthetic point of view here. So what Supremica does is then it take these based on EFA's model, extended finite automata. And you see here typically that there are a number, I think these are just two-state models and some transitions, and so they're extremely small models, all of this, but you see a huge number of models for this application. And I think many of them are just representing specific variables. Then there is a plot here showing all the possible states. So this is not an extremely large system, but then it's actually possible then to also generate a supervisor which avoid these deadlocks. Another aspect of routing, and routing could be in the factory, but it could also be in healthcare, where the nurses are going around to patients. So now we are looking for smart routings out on the roads. And that was actually, it's quite much from Sarmad's thesis here, because he was originally looking at that problem. So home healthcare routing and scheduling is a problem that he was looking at. It was actually only because we started with a specific algorithm, and then we found that, well, okay, it was for routing, and then this healthcare could be a nice application. So vehicle routing problem, the question is then, what is the optimal set of routes for a fleet of vehicles to traverse in order to deliver to a given set of customers? So the objective is then to minimize the travel distance, and this is an NP hard problem. That is a very hard problem. So the first thing you identify here is that you have a number of tasks, and then the question is say that you have 3 nurses, A, B, and C. So which tasks should A take, which should B take, and C? And then, of course, if you have decided that A should take 1, 2, and 3, then the question is how should they travel? So then you have a classical travel salesman problem for each of these routings. And then there is a specific distributed algorithm which, so to say, divide the problem into smaller pieces. And it's called gossip. So from the beginning, based on some heuristics, the division, the task assignment has been made that 3 yellow and 3 red and 3 green. But then we start to test for A and B. Could we find something better just for combining A and B? And then you see down here, it's quite a pure mathematical problem. I think you could consider it as more or less a MILP problem. And then what you see was that 1 node was moved from B to A, And then we look at B and C, if they should be modified, and then one was moved from C to B. And then C and A are tested. And then we found that there was no change anymore. So no update. And okay, it could maybe be tested some more combinations here again before you are sure. But in principle, this is a procedure that is going on for it. It's a definitely suboptimal solution, but it's considered to be very efficient compared to other more traditional methods. So then I'm coming back to this local optimization of automata, which I described before, and here I just have had another example. So in this case, we have two models, G1 and G2, and here we can look for G1, and we have the time going from 0 to 3 is 4. And then we could take this alternative route, and the question is, what is the best solution? And when you optimize the local behavior here, you find that it's best to take B, C, and D. And in this case, A is then a shared event, so that cannot be taken into account. That has to stay there. But for the rest of these events, B, C, D, then this was the best solution. And for the other one, it's best to take E and A. Oh, that has to stay, sorry. And it's best to take F, G, because F, G, and H are local. They are not involved in the other one, while we see that A is shared here. And then you combine these two, and then you get this model. And then it's clear that taking E and then A is the best solution. So going step by step, and in the end, once again, here also you get a very small model, in principle, the initial state, and the sequence of events, the minimal time, and the final state. That is the final solution. What is good here is that you immediately also get the events in this sequence. Actually, this work was developed by another PhD student, and Fredrik Hagebring, and this was just an example from his presentations. But he generally looked at the following situation, where you have an application where you have typically dividing the possibility to divide into zones, in this case only 2 zones, where this truck is serving this first part, and B track is serving this part, and they have to deliver from A to B or the opposite through this place, this house. And the thing is that it was at least Fredrik's experience that this optimization technique needs to have some distinct separation between different areas to make something more powerful, to get very good results. And for this type of applications, he could show that you could make enormous reduction based on when you have a number of robots and you have the number of states, and how much independent these are to each other. I will not explain the details around this, but it just shows that there is a great potential. And at the same time, I think that in Fredrik's work, he did not, he was a bit specialized in his way of thinking. So what I try to do now is to see couldn't we actually consider this as a more generic optimization procedure that could be used for any type of applications? And I hope that my new paper will give a message to that. Now I come to this this application where I mentioned that they had a problem at Volvo with a small software for lane change. And to illustrate this application, which is coming on the next slide here, I just show you here a very simple MATLAB code. So here there is a function called out, which generates, it's called F1, and there is a random generator of this, and if the value of this random generator is higher than 3, then the out is in -1. So that means that the out is one step less than this random variable. Otherwise, you go to this function F2, and in that case, out is instead in +1. So you see, okay, it's an extremely simple behavior of this system, but it still has a function, internal function, etc. And actually, the problem that was recognized in the real software has some similarity with this simple procedure. And here is an EFA describing this. And the first thing is that you get the new value of in by this function call that gives you one transition to, it's actually the whole F1 goes to this state. And then the details of this is that if in is in from this random generator function, if that's greater than 3, then the output variable, the next value is in -1, and this is one event. And the alternative is that you take an F2 call, and the F2 call means that you simply say that next value is in +1 instead. So here you get at least some indication that yes, an EFA can describe a real software with some variables, especially if they are not real numbers, because real numbers are, of course, I mean, then you generate these infinite state spaces and so on. So then you need to have more sophisticated abstractions and so on to solve that. And that is actually something we are working quite hard on at the moment. Let me mention, so I don't forget that, I've talked quite much about formal verification here, but we have to be honest that quite often it's not possible to use formal verification, because when you have continuous variables, I mean, the state space is, even with abstraction, is so huge and so big, so it's not realistic to make this exhaustive search. Although you make that in a smart way with abstractions and so on, it's still too demanding. And then what is done then is what is called formal testing. And testing means that you try to explore different critical areas in the state space. And specifically those areas where you believe that there could be problematic situations, or where, for instance, the code hasn't been tested enough. Because I mean, the problem with all software generation and software testing is that you typically test with inputs that you are expecting and so on, but these expected behaviors, they are typically missed in this manual testing, so to say. So formal testing is another alternative, but in this case they went for complete formal verification. So now this was a lateral state manager, a high-level function, which typically should have control of the state here. And the lateral state manager was, okay, if you have made a request to go in the right or left direction, sorry, in my case it's, yeah, okay, left and right has no meaning here, but okay, left and right, and going in straight forward. Those are the three options here. And the problem was here that they realized that, okay, if you first have made a request, say going right, and then for some reason change the decision, no, I should go left instead, based on the sensor information from the car, etc. Then this functionality around here didn't update. It still preserved the old right decision or right request. So there is an internal variable in this called direction. So it was actually very, very complicated to even find a specification that could analyze the system in a good way. But after some hard work by the master students, in this case, because it was the master thesis work here, they realized that, okay, testing this, if the direction, the internal variable in this lane in this LSM function, lateral state manager, LSM, if the direction is the same as request, then the function works as it should. But if we realize that, okay, you have made a request and you see that the direction is not the same as request, then there must be some error. And they said, okay, if it's only for one time instant, it could still be some initial phase, initialization or problem or so. So that was okay if the next update means that direction is equal to request. But to mismatch between this request and direction means that you generate a blocking state. So in that case, a bad situation has happened. And then you can use this non-blocking procedure to find any blocking states, because this is you could say that in this way we generate a forbidden state, which we should be avoided. So the question, if the system is non-blocking, it's fine, but if it's blocking, meaning that this state has been has arrived, when you combine this specification together with this LSM model, then there is a problem. And exactly how this runs together with the complete software, I'm not exactly sure about, but you could say that this gives a very small picture of the system. But total, this LSM had around about 200 lines of code. So what they had to do was to translate all those 200 lines of code in the same way as is done here, and that was not possible. That was not the big problem, and they could even verify that it was not so to say that it was not a bad translation of that to EFSM. Because when they found the deadlock and the blocking state, they could also realize, okay, yes, there is actually a problem in the software. It sometimes makes these mistakes. So we thought that Volvo should be very scared about this and absolutely not to talk about this. But it's interesting that Volvo Cars is quite open on these issues. So we have even published this result in this case conference, which you have heard about, conference on automation, science and engineering. Because what they mean is that, well, okay, I mean, of course, there could be errors in a software, but they have layers of control of evaluation, diagnosis functions that also test. So I mean, even if this is an error, that should be detected on a higher level. So they were not extremely concerned about this, but of course they agree that we should avoid this type of errors. So okay, by this long story, it just tells us that, well, there is obviously situations where there could be errors in a software, and this technique with non-blocking evaluations based on specifications and translating the code, the software, to extended finite state machines, or EFSM. That is an interesting technique. They also had another timer update, which they realized that 1 of 3 timers was updated 2 times in every loop, and that was also a mistake. And in that case, they could even find a solution to that problem based on Supremic and our tool. That comes on this. So it was a timer increment, and if that comes 2 times before an update, then there is an error. So this was actually an easier problem to handle. Okay, here comes this robot application where we had this plates that should be joined together. I mentioned about that in the first seminar here. That is this is a PDF presentation, and that is in a movie. And if we have time, I will show a movie on that later on, and that also had some ideas around reinforcement learning, that as I mentioned before. Well, here I just want to show that of course at Chalmers we are working a lot with Volvo Cars on safety issues and autonomous driving. And this is a well-equipped Volvo XC90 with a lot of sensors and so on. And here there was also an evaluation of self or an autonomous driving situation, and a lot of sensors around, as I said. And here the focus is on how to avoid pedestrians. And here they have different zones representing the future of the pedestrians. And here is one pedestrian, and the expectation is then that, okay, that pedestrian should pass away before you can cross. But here another one is coming, and then the idea is that the vehicle should be able to pass path before that vehicle is crossing. So this problem is evaluated here with this model predictive control. And it's not something I've been working on myself, but I just want to show you that there are optimal control problems related to safety issues in autonomous driving, which we have looked at in our division, especially in the mechatronics group. I would say that because we have also had an adjunct professor from Volvo Cars and the sister companies there, who is one of the true experts on autonomous driving, on the autonomous driving development at Volvo Cars, and also earlier the safety functionalities. There is something called city safety, which means that a Volvo car should be able to stop in front of a pedestrian, even if it's going in 30 kilometers. So immediately it should be able to stop. Yeah, this has worked fine in most situations. Unfortunately, Uber had a car accident, but yes, in that case, Uber did not use Volvo's software. They tried with some own software, and then unfortunately a woman was killed in a car accident. So it was not good advertisement for Volvo in that situation, but that's life. And then what I would like to say here, that many of the this safety functionalities which you have in the Volvo car, they have been developed together with our PhD students in my division, especially in the mechatronics group. Yeah, then another area which I maybe should have mentioned in my presentation at the seminar, because I heard that someone was interested in cyber physical system and security functions. So I will just briefly mention about that here. I don't think I have said much about that. Maybe I've mentioned it in very broad perspective, and it's not very detailed here, but I will at least show you the mechanism for fault diagnosability and opacity. So of course, any unwanted behavior, faults and so on, should be able to diagnose and avoid. So machine fault, sensor and actuator faults, communication error, software bugs, etc. It should be able to find those faults. And opacity has to do with secret aspects. If an intruder comes, is it possible for an intruder to detect some security knowledge in a system? And another one is anonymity. So you would like to have some location-based privacy. So it should not be able to detect if a person is in a specific location. So a very basic question in diagnosis is, first we can say that generally a diagnoser is given an assumption that you have a model of the system. Then a diagnoser is built by generating what we call an observer. An observer take into account that some events are not observable, and then they have to be joined into block states. And this observer generation is quite straightforward. Its complexity is a little bit bad, but the observer in itself is quite easy to construct. Then the question is, if you have such an observer, is it also possible to then observe errors? And if that is the fact, then the system is diagnosable. If not, then it's not diagnosable. And of course, it's very bad if the system is not diagnosable related to the faults we have modeled in the system. And you could then say that, well, I mean, how could you say that you could model a fault or an error? But then you could say that at least, yeah, I mean, the assumption is that sometimes you can also introduce, of course, then unobservable fault transitions. But it could also be that as soon as you get something that does not follow your original automata model, then you assume that, well, this is outside the behavior of the system, and then you report that as a fault. So that is a more easy situation. But here we have the assumption that, well, okay, you have first this state 0 and then 1, and after that either an unobservable event but not a fault event brings us to state 2, or a fault event brings us to state 3. But in state 3 you get you have a self loop, so sooner or later you will get a C event here, and in the good state you have a B event. So you could say that as soon as you detect a C event, then you know that a fault has happened. So that means that after a number of steps in the automaton, you can guarantee that an event happens by which it's possible to recognize that an error has happened. And that is called, if that is valid, then it's said that the system is diagnosable. The opposite, how is that? Well, if the situation is that both the unobservable and the fault brings you to state 2, where you get an event B as a self loop. Then when you get a B, you don't know if it was an unobservable event or if it was a fault event. So this is the most simple illustration of a system that is not diagnosable. And then you can generate special functions that can, for an arbitrary model, for an arbitrary system, analyze if the system is non-diagnosable or if it's diagnosable. Because if it's non-diagnosable, then you must change the model in some way to reflect this. Or maybe you need to add some new sensor and so on. Then we come to the state opacity, and current state opacity is as follows. The idea is then that an intruder actually could have a model of the system, which is quite strong assumption, but assume that. But it only has the observable events. That can be reported. So the thing is then that, okay, if is it possible for an intruder, based on the observable events and a model of the system that is available, is it possible to be sure that the current state is a secret state or not? So and then we can say that current state opacity means that it's a good situation. That means that an intruder is never certain whether the current state is within the set of secret states. Okay, the intruder knows where the secret states are, but it can never say for sure that the current state, in that case, in the observer, includes only secret states, because in that case this state, the system is not current state opaque. So what you do then is that you generate the observer and you see if is there a blocking state in or blocking state. Okay, it sounds bad now. Not blocking, a block state, sorry, a block state that in the observer that only includes secret states. Then if the intruder has generated the observer and follow up with the events, then it can be sure, now someone is in a secret state, and yeah, that is not a good situation. I am a little bit critical on this because I mean, what is this really an important and relevant problem? And I have I think this is a little bit too academic. but it's a lot of activities around this at the moment. So one possibility to solve this problem is to identify situations where you have unique states, block states in the observer, which only includes secret states, and they are then called non-safe states. And then what you do is that simply you are looking for non-safe states in the observer. And okay, there are some connections between opacity and diagnosability. Okay, yeah, here is a simple example. So assume that that state 0 is a secret state. Then if you generate the observer for this system, which means that in this case you cannot distinguish between state 0 and 2 if you start from the beginning, because if U happen, then you are in state 2, but that is unobservable. If transition A happens, you know that you're in state 1, and if B happens, you know that you're in state 2. If the secret state is state 0, then it means that, okay, when you look at the observer, you don't have any state here, block state, where you only have secret states. So that means that this is opaque, while this is non-opaque, because if the secret state is both 0 and 1, then this is a non-safe state, because if an A happen, you know that you are in state 1, and that is a secret state, and it should not be possible to detect that. I think it would be better to have changed this to the secret state is 1 in this case, and in this case the secret state is 0. Okay, doesn't matter. What I indicate by this is that generating these observers, and based on that you can make at least some interesting analysis on security aspects, and I think this will be developed further to more realistic scenarios. The final application I would like to talk about, we have 10 more minutes. It's the robotics, AI, and healthcare. And here I give you some pictures of people which I worked with. Christopher for many years. He has worked with me both on the robot energy consumption sequence planner, sequence of operations, and so on. Unfortunately has moved now to Volvo Trucks, but still we will collaborate with him. And here you have 3 new persons that I've recruited more very recently, I would say. Karin and Emmanuel, they are married, and they are coming from Mexico from the beginning. And especially Karin is focused on the high-level aspects of robots, humanoids, service robotics, and so on. Jasmine, she's also within this field on AI. She is, we could say, the best on machine learning, and also the specific problem of grasping parts, which is definitely a challenging thing. So Christopher, he has worked for quite a number of years together with the emergency department at one of the hospitals in our region. And that the initiation of that was because he met one time by a coincidence when he was running for training exercise out in the wood, and then he met a person from this hospital, and they were starting to discuss what kind of information that would be useful. And then they realized that, okay, we have worked, or Christopher has worked with sequence planning and information for factories, but it is the same kind of problems and interest also in especially emergency departments. And you know, I've been not so many times, but a month ago I was with my 91-year-old mother at the emergency apartment at the hospital, and you have to sit there and wait and wait and wait. And you know, don't know exactly what will happen. When will the doctor arrive? I wouldn't say it was extremely bad in that situation, but of course, if there was an idea that, okay, the plan is that the doctor will arrive in say 10 to 20 minutes or something, it could be a good information for the patient, but of course much more for the nurses and those who are planning the activities. How is it with all our rooms? Are they busy? How is it with all our doctors and all our personnel here? Where are they, and what kind of prognosis do we have for when we can get different activities performed here? And you can say that these emergency departments, they work very well in most cases, but when it gets chaos, then yeah, it's really chaos, and sometimes that happens. And then Christopher introduced quite a simple procedures in information on the computer that they actually are very happy with, and when he has this server has had his server at his room at Chalmers, and for some reason when that server went down, they called him immediately and said, oh, it doesn't work. So it was something very useful for them. And this just illustrates a little bit on what different I think the rooms here and the patients and waiting for doctor, and I mean, based on this you can also get a lot of statistics and so on. So sequence planner at the emergency department in Trollhättan. It's a city 70 kilometers north of Gothenburg. And actually this activity is something that has also been it's a lot of interest in this planning to make more efficient planning for other departments. So for instance radiology and also some other departments with a lot of expensive equipment for X-ray, etc. There, this type of facilities is of really great interest. Yeah, I mentioned that Yasmin, that she's interested in this robot grasping and manipulation. So this is just some pictures showing some challenges here. I don't make any further comments on that, but grasping is definitely an issue that needs to be taken care of. Micro manipulators in biomedical applications is of course another more or less classical problem. Here you see TUM, so it's not a problem we have worked specifically in our group yet, but Karin and Emanuel, they worked at TUM in Munich for a number of years, so that's something they have brought up from there too. The last application here is quite interesting, and it's related to rehabilitation. So say that a person have got stroke, and then it's hard to move, for instance, an arm or something. So then you could add an exoskeleton to that arm, which could support in the beginning with quite large torque to get huge assistance for that arm, because the muscle is not okay. But after some time, when the person has trained, it's important that this exoskeleton does not support for a long time. So this torque need to be adjusted. So after some time, you need to have small torque and reduced assistance. In the end, of course, the idea is that you should not need this at all. So some kind of adaptation of this torque here. And the idea is then to, here you see some of these actually equipment. The idea is also to use this robot skin in this phase. Actually, I'm not sure exactly how that should be done, but the idea is to make very nice exoskeleton, which is very flexible and comfortable to use. So that was the last picture there, and then the question is, I have some more things, but maybe it's enough with this, or what do you say? We have some questions here now.
Yes, Professor. Very interesting.
How appropriate is it to use logic control and automation in case of network routing problems, given the huge dynamic and complex nature of networks? How can the huge packet losses or missing of some events and positions in the corresponding model automaton be incorporated and carried about? Yeah, this was tough questions. I'm not sure if I have any very good answers to this. Packet losses, missing of some events and transition in the corresponding model automaton be incorporated. I know that we have simply introduced package losses in some MDP models, or Markov process models. So, I mean, of course, that means that there must be some possibilities to detect that. And I mean, if this is not, so to say, observable, then you must have some indirect information that gives you a detection that you have lost data packages. So I think that's the only thing I can tell about that. The first question, how appropriate is to use logic control and automation in case of network routing problems? I have always thought that this is an interesting area, and for some time I had some discussions with Ericsson on this, because Ericsson has a big group of people here in Gothenburg too. Ericsson, you know, they were very early to build mobile phones, but they are not doing that anymore. But it's more the network around that they are big on. I mean, of course, there are routing problems there that is of interest, but I must say that I cannot. I mean, the problem you indicate here, that it's a huge dynamic, and of course the question is, if you say, should you go in the A direction or in the B direction? Yeah, I mean, there must then be some measurements on, so to say, how is the buffer size at the moment, and based on those kind of information, you can also make some probably optimization based on that. But I'm sorry, I'm definitely not an expert on this, so I don't think I can give you any good answers to that.
Okay. Thank you, sir.
Do we present subjective decisions in the language of automaton? Well, you could say that the only thing I can relate to this is that I mean, that all things here are either based on a model, and I mean, if the model has a subjective decision in it, then it's fine. And then you could say that these notions on uncontrollability is a way to open up for a freedom where you don't know exactly what the user will, which decision it will take. But if it's very personal decision made by that person, and another person has another way of acting, yeah, that's of course a tricky problem, definitely. And you could say that in that case, actually, then maybe I should show you a movie. I could end up with a simple movie, because that illustrates human interaction with the robot. And then you could say that reinforcement learning and those kind of things could be helpful to bring up what kind of decisions that a human takes in this area. So let me take that as the last thing here.
Sir, I mean to say that
Yeah?
can we use the fuzzy logic to describe such type of states in the automaton?
Sorry, which
Can
type
we are using the patty nets as we can say as a language to describe the automaton. Is it right?
You mean to describe? What did you say? The language, or the what? Repeat the question again. Sorry.
The language which is used to describe the automata. We are using the patty nets. Is patty net one of the language, or we can say it is a descriptive language in terms of a network?
Of course, you can use Petri nets and modular automata for your network. I mean, those are classical models used for that. Yes.
Yes. But for the subjective type of the we can say the things like fuzzy, we prefer for when there is an uncertainty in the decisions or in the state. So can we use that fuzzy sets, or we can say the fuzzy operations, to represent the subjectiveness in such type of situations?
Yeah, I mean, then I think that the learning procedure is what we need to look at, and then you could say that yes, we have started to look at the possibility to use learning for generating these automata. So you remember I said when earlier in the discussion here that okay, it was a discussion on how easy is it to get all these models, and how huge are they, and then it's even possible to generate small models by learning procedures. But even in that case, of course, it's a challenge, because in that case we assume that we have a simulator of the system, and that, I mean, a simulation of a model is quite often what we have, and in that case you can, based on that simulator, trying to automatically generate an automaton. But that was not exactly what you were asking for, because you mean that okay, a human can take different actions and different humans can take different actions. And then could I just show you this movie here to see what you say? Okay, then I should. Yeah, I have too many open windows at the moment.
Hello, sir.
I need to stop sharing first here. Yeah, no, okay, no, I can do that. Yeah.
Shall I continue my question, sir?
Sorry?
Shall I continue with my question, sir? Shall I continue with my question, sir? Hello.
Yeah.
Hello, sir. Actually, I was reading one paper on the SCADA system. Hello.
Yeah, please
I
go
was
on.
reading one paper on the SCADA controller design for power system problem using the
Okay.
hybrid automata modeling. In that paper, it was written that there are three types of the, we can say, descriptive languages: fuzzy logic, Petri nets, and the modular automata. So that's why this question, ultimately, they have not used the fuzzy logic in the paper, but they have mentioned this thing in their paper. So I was asking that whether we can use that. Was why this question came to my mind.
I would say that fuzzy logic could definitely be of interest when you have these hybrid aspects, when you have some continuous variables around, then fuzzy logic can definitely be of interest. If you have a combination of pure logic and continuous behavior, then this fuzzy could at least be one option. Yes.
Okay, thank you, sir. Thank you so much.
Let me then switch to this. Let's see here. So the idea here is that first, the question is about safety in human-robot collaboration is important. And then, of course, different humans could act in different ways, and then the idea is that one should, so to say, a supervisor or a control function, an agent here should learn this behavior. But of course, safety aspects are of great importance here. For instance, that the robot should not move too quickly when the human is close to the robot. So it could be that one rule could be that the robot only is allowed to move very slowly when it's in close to that. Okay, so you could set up different scenarios and different restrictions, and then the question is, can you even use reinforcement learning to find if there are any bad behavior in your algorithm for safety hazards? Then, you know, in this formal testing, then they are talking about falsification. Is it possible to find any bad behavior or false behavior in this? So reinforcement may be used for quite difficult word, falsification, in which the worker is controlled to behave as risky as possible. Yeah, I mean, the problem is that when you develop these learning facilities, it's typically that you learn the good behavior, but the risky behavior is not always picked up. At the same time, it should be relevant behavior that is evaluated. And what the following now will illustrate is that with standard reinforcement learning technique, it will not work very well. Standard Q learning may produce irrelevant behavior. Let's see if I can let this. Yeah, okay. So you see that it's more or less the same type of actions when the human click on that starting, or I think it's the safety button. So yeah, it's just crazy behavior, and that means that the exploration of the problem is not good here. So then they tried quite hard actually to find a solution to this, and one way was to introduce, you remember that I was talking about reinforcement learning, and to add temporal logic into that to guide the exploration in the search space, in the state space search space. And that together with, I will soon show you a movie again, and here we simply introduced, instead of temporal logic, we found it easier to introduce an automaton specification directly, which where it was one specific forbidden state that should be avoided. And then also to this was added Lagrangian relaxation, which is a topic that is often used in general optimization, and also I mean reinforcement learning is also a type of optimization. So it's a very new idea that have been published very recently on how to introduce this Lagrangian relaxation to get better exploration. And once again, this exploration problem is a huge problem in reinforcement learning. But let's see what happened in this case when he introduced those elements. Okay, sometimes he puts in the green button, but then he goes to fetch a new piece, and yeah, now it works more in the expected way. So you could say that to generate falsification is still possible, but you get more of, so to say, the normal behavior into the system. And the problem with the first solution was that it was totally irrelevant behavior that was only evaluated by that procedure. So you could say that this illustrates that reinforcement learning is not that simple. Okay, you could say also that this falsification problem is a very specific problem, which is quite tough, but it's related to this verification of software. So based on that, yeah, okay, here one could see that with this reinforcement learning and this automata-based, much more of the state space was evaluated. You see more of green dots here, and that means that you have evaluation more of the complete state space, while ordinary Q learning just is moving around in a more local area here. Yeah, I think that was enough. So stop there. So by that, I would like to thank you very much for joining this course, and I have to be honest that it was not a perfect contribution from my side. It was quite theoretical, but it was unfortunately tough because I had this other deadline also. And I realize now when I look back on this MATLAB functions that I could have spent more time showing a bit of that, but at least you will get this 4 or 5 or 6, yeah, let's say around 10 MATLAB functions that you can play around with as best as you like. Okay, by that, I would like to thank you very much.
Thank you so much. It was indeed a wonderful course, and I'm sure that's going to be rich material for all the participants. Participants, now is the time to give your feedback, tell us whatever you want to tell. And before we go ahead with the feedback and the valedictory, I would like to tell that, Professor, that you have given a very good prelude to my next course, GIAN course on human-centered robotics. So that is, at the end of your slides, you gave some examples of grasping and then healthcare, or AI and IT for healthcare. So my next course is starting from 9th of May. Yeah, that's on human-centered robotics. Participants, you can find out on GIAN's portal. Okay, with this, on behalf of my colleague, Dr. Shravan Mohanty, and myself, we sincerely thank you. It was a wonderful, great experience for both of us, and I hope for all the participants as well. Although GIAN portal, I find that it has a lot of difficulties in registering. So we could not get many participants, but there are a couple of people who have been very actively asking questions. I'm sure that they have something to say, and others who have been remaining quiet. You please feel free in telling us about your experience with the course. Thank you.
Okay, thank you very much. And I guess that I mean, this evaluation is something you have without me, because then people can be more open.
I don't think so. People would be definitely willing to thank you, sir. And may I request all of you to please open your cameras. Let's take a last group photo with our professor. And thank you so much for giving your time and so much, of course, material, sir. We hope that we will continue to have your support to our courses in future. It was to be done through a physical mode, where you could have seen our undergraduate and graduate students as well. But because of this is their examination last month. So they have not registered, in fact, but we have people from all across India.
Hello, ma'am. I would like to say something. Hello.
Yes, definitely, we are inviting you to.
Yes, ma'am. First of all, I will thank Professor Bengt to give such a wonderful, we can say, the course content and the delivery of the course content in a very nice way. So actually, I'm the new person in this field. And this is the one area which has continuously, I can say, I was searching for that I should learn something about AI. Long back, I have studied about this course during my post-graduation course as a part of, you can say, soft computing or something like that. One unit was there, but I was not able to understand it in a proper way. But I have, through the research papers, I have seen that for some type of the problems, the people are using this AI, type of the networks and the logic proposition or predicate logic, something like that, they are using in the power system as well. And secondly, as we have started a new program in electrical and computer engineering in our institute, so there was a course on AI, specifically on AI. And the responsibility was given by my head to me that you have to run this course for the students. So this was a very good opportunity for me, at least to learn to start with this course. And I from your the videos as well as from your course material, definitely I will build up this course. And I would like to, I could say, like to supervise one MTech thesis in using this AI, or we can say this hybrid mode automata in the power system engineering problems. Thank you so much, Professor Bengt. And also, ma'am, I would like to congratulate you, although your health was not good from last 1 week or so, but very well you have run this course in a very nice way. Thank you, and congratulations to you and your team. Thank you so much.
Thank you.
Thank you.
Sir,
That
sir,
means
your
the
team
course
is doing
successful.
very good work. Very good work your team is doing for not as at a research level, but also we can say for society welfare at large. Congratulations to your team, sir. Thank you so much.
Thank you.
Thank you so much. That means, Professor Bengt, you have now seen that the course was really successful. If even one person can develop a course based on this and can learn, I think that was the main goal of this course. Thank you so very much, ma'am, for giving your inputs. Any other person who would like to say something? Now our director, Professor Kondekar, has also joined. I'm so thankful to you, Professor, for
thank you very much.
your
Am I audible?
for giving it. Yes, very much.
Oh, thank you.
And we had a wonderful lecture by Professor Bengt on for the institute faculty and students.
Right.
Although today was the New Year, so not many could join. And but thank you so very much. Would you like to say something?
Yeah, let me congratulate you at the outset for organizing such a great course for all of the participants. And I would like to thank Professor Lennartson for giving his valuable inputs on AI logic planning and learning for controller design, basically, which is very important because nowadays everybody is talking about machine learning, AI, and all that. But this course actually focuses towards practical implementation in automation and so many things which are very important for electrical, electronics, and other core branches also. So really great. I have seen some of the inputs, some of the course I have just watched, and I came to know the feedback just now from Dr. Manbir Kaur. It was really useful to most of the participants, and building a new course for our curriculum will be quite helpful. I'm looking forward help from Professor Lennartson, as discussed earlier in inauguration, that from Chalmers University's key important subjects like quantum computing, graphene, these are the leadership from that Chalmers universities. So our institute needs a great help from you in that regard also. So thanks a lot, and once again, congratulations and thank you very much, Professor Lennartson. And we are looking forward for your continuous support in almost all possibilities which you can expect that we can collaborate with each other. Thank you, madam. And I also congratulate all the participants.
Thank you very much.
Thank you, sir.
Thank you, sir, for your kind words. Really, giving time is the most precious thing in this world, and that is what Professor Lennartson has done for us. And I'm sure that one or two from this group are going to take it further. And as Dr. Manbir Kaur has said that she's going to develop the course around this, that's wonderful. Anyone else who would like to say something? Okay, so there are people, yes.
I'm seeing two Manbir Kaurs here.
One is Dr. Manbir, you must have.
Yes,
oh, okay. Oh, there is one more Manbir Kaur.
She is the same.
Okay, okay.
Actually, sir, my laptop microphone is not working. And yesterday I had some problem asking the question, so I switched on my mobile phone as well to talk.
Great. Thank you very much.
One is keeping silent. So
yeah, one is kept silent. Yes.
With this, we say that the course is complete, and we look forward to your support in future, sir. And we hope that you will find time to visit our institute in future as well, if everything goes fine, for some other on some other occasion. On behalf of Indian Institute of Information Technology, Design and Manufacturing, Jabalpur, we sincerely thank you. And we also thank all the participants who have been attending the course and who have been asking questions as well. Especially Dr. Manbir Kaur and Deepojwal. Both of them have been very active throughout the course, and they have asked very good questions which have made us learn better as well. So, Shravan, would you like to say something?
I would again like to thank all the participants for being here for this course. But we wanted to run this course in physical mode, but due to certain issues that it could not be materialized. But I hope in future courses, you guys will definitely visit our campus at least. We have a very nice campus, and Jabalpur is a very nice city. So you should visit in our future courses, or maybe we periodically organize conferences, then different courses, and hopefully we would like you to visit our campus. It's a beautiful campus to see. Thank you all.
So in these 10 years, Professor Bengt, the campus has been developed, and now Professor Kondekar is leading the institute. So we hope that you'll find time to come. Thank you so much, all of you. We hope that this network will remain active. We will continue to work, and we will also find out possibilities of collaboration. Thank you so very much.
Yeah.
Thank you.
Madam, this course material is already made available to all, right?
Yes, Professor has done, he has done a lot of work. He has given his course notes and all the lecture notes as well.
Wow. So kindly send me one copy. I would like to go at my leisure time.
Will be. Yes, thank you.
Thank you.
Yeah,
thanks a lot.
The last lecture I will also deliver to you.
Thanks a lot.
Thank you. Bye-bye.
Yeah. Thanks a lot.
Bye. Thank you. So I'm ending the meeting for all. I hope you've taken the photographs. Yeah. Thank you, Professor.
Thank you.
We can't thank you enough. In fact, it was such a wonderful time we spent with you.